Today I'll be presenting my work on optimizing the Hamiltonian path problem using a genetic algorithm enhanced by wisdom of artificial cross, or GA for short. This project focuses on applying and improving evolutionary techniques to solve a classic NP complex problem that has significant real-world applications. I'll discuss the methodology, parameter tuning, results, and possible future directions for this research. So the Hamiltonian path problem involves finding a path through a graph that visits each vertex exactly once. This problem is classified as NP-complete, meaning that finding an optimal solution is computationally intensive as the graph size increases. This is especially challenging for practical applications like logistics, where finding the shortest delivery route between multiple cities is crucial, or network planning, where efficient paths can lead to cost savings and improve connectivities. Given its complexity, traditional methods struggle to keep up, particularly as the number of nodes grows exponentially. Our goal here is to find a better way to solve this using advanced heuristic. The primary challenge of solving the Hamiltonian path problem lies in the exponential growth of possible solutions as number of the cities increases. For instance, with just 20 cities, there are 20 factorial possible paths, over 2.4 trillion combinations. Evaluating each path one by one is impractical with this level of complexity. For larger instances, a brute force solution would require an enormous amount of computational time, making it unsuitable for real-world applications. This challenge drives the need for more efficient methods like genetic algorithms, which use a guided search to quickly hone in an optimal or near optimal solution. A genetic algorithm, or GA, is a heuristic optimization method inspired by a theory of natural evolution. It starts by generating an initial population of random candidate solutions. These solutions evolve over multiple generations through three key processes: selection, crossover, and mutation. Selection involves choosing the fittest individual, those with the shortest path. Crossover takes these selected individuals and combines their genetic traits to create offspring, ideally inheriting the best aspects of both parents. Mutation is used to introduce random variations, maintaining genetic diversity and allowing the algorithm to explore new solutions. Together, these processes guide the search for the shortest path in the Hamiltonian path problem. To prevent the genetic algorithm from getting stuck in local optima, a common issue in evaluationary algorithms, we introduce an enhancement called wisdom of artificial cross, or WAC. WAC is based on the idea of combining insights from independent subgroups to find a more robust solution. In RGA, the population is divided into smaller subgroups that evolve independently. After a few generations, the best individual from each group are merged back into the main populations, effectively pulling the collective wisdom of the independent subgroups. This approach maintains diversities, encourages explorations, and prevents premature convergence to suboptimal solutions, ultimately leading to better quality outcomes. Our hybrid GAWAC approach begins by initializing a random population of possible paths through the cities. We then evolve this population over several generations using selections, crossover, and mutation. At regular intervals, we divide the population into smaller subgroups, each evolve independently. This independent evolution fosters diversities and reduces the risk of premature convergence. Once the subgroups have evolved, the best solutions are merged to form a new, diverse wisdom population. This ensures the entire population benefits from the strengths of each subgroup, making the search more effective. To better understand how the GWAC operates, here is a breakdown of the pseudocode. The process begins by initializing a population of random solutions and evaluations their fitness. Each generation involves involving the population independently in subgroups, using crossover to combine parent solutions and mutations to introduce variations. After evolving independently, the best solutions are merged into a wisdom population. Selection, crossover, and mutation are applied again, and the process repeats for the specified number of generations. This pseudocode captures the iterative evolutionary nature of the algorithm, with an emphasis on both exploring the solution space and exploiting the best known solution. One key to make the genetic algorithm effective is parameter tuning. The parameters we focused on were population size, mutation rate, and the number of generations. We tested population size of 50, 100, and 200 mutations rates of 0.05, 0.1, and 0.2, and ran each configurations for 1,000 generations. Larger populations provide more genetic diversities, which helps explore the solution space more thoroughly. On the other hand, mutation rate controls how frequently random change are introduced, which helps the algorithm escape from local optima. The objective was to find a good balance between exploration, finding a new possible solution, and exploitation, improving the current best solution. For testing, we used a distance matrix representing 20 cities. Each element in this matrix was a random integer between 1 and 100, representing the travel distance between two cities. This kind of data generation simulates the unpredictable nature of real-world distance. Importantly, the diagonal of the matrix was set to 0, since there are no self-loops. A city cannot connect to itself. The randomness of this test data allow us to rigorously evaluate the GWAC's ability to find efficient paths through various and realistic problem scenarios. The result of tuning GWAC with different parameter combinations were insightful. We found that larger population size led to a better outcome. The configuration with population size of 200 and a mutation rate of 0.05 consistently provided the shortest path. The convergence graphs, which plotted the best distance over generations, showed that these larger populations reduced the risks of premature convergence and allowed the algorithm to reach a high quality solution more consistently. A mutation rate of 0.05 introduced enough variations to explore new paths while maintaining stability during the convergence. So use the GWAC approach, we were able to identify highly efficient paths that minimized the travel distance between all cities. This connect network graph visualization represents the optimal path found. We can see that each city is visited exactly once, ensuring minimal distance while covering all nodes. The parameters set with a population size of 200 and a mutation rate of 0.05 provided the best of solution. Larger populations consistently resulted in a higher quality solution because it offers more diversity, which reduced the risk of getting trapped in a local optimum. Lower mutation rates, such as 0.05, provided enough explorations while allowing the algorithm to stabilize around promising solution. Higher mutation rates cause instability and more oscillations in the convergence plots prevent the algorithm from effectively focusing on the best solutions. So the GAWAC hybrid approach effectively solved the Hamiltonian path problem, providing high quality solutions in a computationally efficient manner. By enhancing a traditional genetic algorithm with the wisdom of artificial cross, we maintained a high level of diversity, which is crucial for avoiding premature convergence. Fine-tuning parameters like population size, mutation rate, and the number of generations was key to maximizing performance. So the next step in advancing this research involves exploring further parameters optimizations to enhance the genetic algorithm's effectiveness. One promising area is use of the adaptive mutation rates rather than using a fixed mutation rate throughout the evolution process. An adaptive rate would allow for more explorations in the early generations and less randomness as algorithms converge, enhancing both the quality and efficiency of the solution. Additionally, implementing advanced algorithm strategies could ensure that the best solution from each generation are retained and refined further, providing a mechanism to speed up a convergence without losing solutions quality. Other focuses on for future works is to investigate a new method for maintaining population diversity. Techniques such as crowding, speciation, or diversity preserving selection schemes could help prevent the algorithm from converging prematurely on local optima, especially when dealing with large complex problem spaces.